Shape optimization using genetic algorithms. What is shape optimization? Shape optimization is a process of finding optimum values for the geometric design variables which will give the optimum shape, meaning these design variables will help in creation of the shape such a way that it satisfies the given constraints and optimizes the specified objective functions. So this shape optimization needs following following components. One is shape generator. So based on the value of design variable value, based on the design variable value, we need to have a shape generator to create the shape, and then generally we will use this computer aided engineering. It could be for the finite, it could be for structural mechanics, or it could be for thermal, fluid, or anything. So depending on that, we need to make a mesh uh, based on the shape which is generated, and then we should have a physics solver. It could be a FEM solver or it could be a CFD solver depending on the situation. And then we need to have a objective function evaluator, generally the solver and the post-processing tool which will give you the objective function evaluator, and then an optimizer. The optimizer could be of any type. It could be gradient based or it could be evolutionary. Okay, let's take an example problem of a cross flow heat exchanger. Okay, so in cross flow heat exchangers, there are hot tubes which carry the main fluid, and then we have the cross flow, which is generally an airflow uh, passing over the hot tubes. So as the air passes over these hot tubes, the bank of hot tubes, the tubes get cooled. So this way the cross flow heat exchanger works. But generally the tubes are circular in shape, but we may not know is this the optimum shape. So when I say optimum shape, what I mean is the heat transfer from the hot fluid to the air should be maximum, but the pumping power or the pressure drop occurring due to the airflow should be minimal. So that is what I mean by an optimal cross-sectional shape for the hot tubes. Okay, so in this case, we will use the non-dominated sorting genetic algorithm, NSGA2, for this purpose. And here, if you ask me the physics, what are the equations governing it? It is going to be a Navier-Stokes equation and energy equation. Okay, so the 2D shape of the cross flow heat exchanger is shown here. So here you have this uh, a series of hot tubes represented by elliptical in shape here, and uh, and then on the left hand side you have the airflow inlet which is coming in at a specified velocity and a specified temperature, generally ambient conditions you can say, and then it flows from the left and then it leaves um, out of the domain on the right hand side with some increase in air temperature. Okay, and for this computational purpose maybe we can even take uh, one segment of this heat exchanger which is marked by the blue rectangle here, and we can specify on the top and bottom symmetry conditions, and then we can assign a fixed wall temperature for these hot tubes. So thereby you are not actually modeling the inside main fluid flow within the tubes, but we only consider that the tubes walls are at some specified high temperature. So yeah, so what is the how to implement this shape optimizer? Like what are the steps involved in the shape optimizer? The first step is we need to generate the population of design variables. So this is GA based algorithm. So first step is we need to generate the population of design variables, and then we need to evaluate the objectives for each of the population. Okay, so in order to evaluate the objectives, we make use of this ICM CFD and Fluent solver setup. So for each of this design variable value, we create a new geometry and we mesh the geometry, and then we supply it to the CFD solver, and solver solves it, and then it evaluates the objective function and gives it back to the genetic algorithm optimizer. And based on the objective values, the optimizer ranks the population, and then it chooses a suitable parent. Okay, so it generally, during the parent selection, it will ignore the the population which has given a very bad objective values, and it will choose only the good yielding population as a parents. And then from the parents, new set of offsprings will be produced. So for this, you can either use crossover or mutation techniques for the offspring production. And then and then we need to evaluate the objective values for the offsprings. So for this, again, we call the ICM CFD and Fluent setup. So with the help of that, we can evaluate the objectives, and then again rank the parents and offsprings. Um, from the mix of parents and offsprings, pick the top performing um, design variables as a new parent, and if the maximum number of generations are passed, and then we supply this as an output values, and if you have still more generations to do, then these new set of parents are passed on to this step, where again we do the offspring production, and we evaluate the objectives, and then create a new parent, and then this um, goes on till you reach the maximum number of generations. So we need to choose the generations in such a way that it is sufficiently large enough to assess the whole spectrum of design variables, um, as well as it is not time consuming. Okay, so a little more into the optimization details. So the objectives in this cross-flow heat exchangers are, one thing, we need to maximize the heat transfer. So that can be measured by the increment in air temperature. So we want to maximize the air temperature. So that is one possible objective. The another possible objective is we want to have a minimal pumping power for the air. So we need to have a minimal pressure drop over the shape. So these two are the objectives. So it is a multi-objective problem. And so here the design variables, in the case of a shape optimization, generally people will take geometric parameters like, say, the diameter of the tubes, or the diameter of the tube, or radius of curvature, or width, breadth, length, and these are as the design variables. In this case, we have taken XY coordinates of the control points. XY coordinates of the control points. So so each tube, I mean, actually we are modeling only half of the tube, so because of the symmetry conditions, so each tube will have 4 points, and this B-spline curves passes through these 4 points, and the first and last points, which are lying on the symmetry line, are fixed, so they don't vary in nature, but the 2 points, they will vary, and so depending on its position, you get a different tube shape. So in total we will have 12 control points. So the number of design variables is 12, and for each of the design variable, say x1 and y1, we specify the lower bound and the higher upper bound. So that is xmin and x1 max. Similarly for y1 and y1 min and y1 max, and so on for all the 12 variables. Yeah, and then we use ICM CFD for mesh creation. So general mesh size for this scenario is about 40,000 elements, and we solve this thermofluid problem using Fluent Solver. Okay, so uh, this optimization problem was ran for about 20 generations, and the population size is 30. So which has yielded a good result. And so since it is two objective optimization problems, the results are plotted um, of all the samples of generation, all samples of generations are plotted here, and the last generation design variables are marked by the black plus points. So that is the best performing one. So because it is evolutionary, so uh, the next generation of population will be better than the first population. So um, the last population is the best population. So that best population is represented by these black plus marks. And so this Pareto parent, which is having delta T in the x-axis and delta P on the y-axis, shows that increased heat transfer comes from increased pressure drop. So as the tubes becomes thicker, the heat transfer increases as well as the pressure drop increases. And so here, in case if you want minimum pressure drop, minimum pumping power, then you can go for this almost a biconvex shaped tube. But if you're okay with slightly higher pumping power, then you can go for this teardrop shaped tubes, which yield higher delta T as well as delta P. Thank you.